Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video, Inverse Hyperbolics in Calculus. It's a topic we will give only minimal and cursory examination since you don't see too much of inverse hyperbolics in calculus, especially integral calculus. You see it more so in differential calculus, and likewise we don't have to put too much effort in this, just a cursory examination. You know what an inverse function is. Any function, if you're starting out with, it will have an inverse if that original function has a one-to-one relationship or correspondence with regards to domain and range. If there's a one-to-one relationship between the domain and range, it will have an inverse. If it does not have a one-to-one, you might have to limit the domain to find that aspect for which you can see one-to-one aspect, then you can determine its inverse. How can we demonstrate this one-to-one or lack of one-to-one? You can see it best in terms of this. If you have in a curve any point where you're seeing something like this, plus and minus x giving you a y value, two different x values giving you the same y value, you lose the one-to-one relationship and you fail a horizontal line test. Think about a parabolic curve. If you have a minus x value here and you look at a positive x value and you look up over here in terms of the range, you can draw a horizontal line at more than 2 points. In each of these instances, two different x values have the same y value, so you don't have one-to-one correspondence. But if you look at a cubic function, you have a minus x value here and you have a positive x value here. It could be minus 10, positive 10, minus 5, positive 5, but you look in terms of their range. Here you'll have a x comma y, here you'll have a minus x comma minus y, and you have one-to-one, and there's no horizontal line that will cross at more than 1 point. Here a horizontal line crosses at 2 points, so you fail the horizontal line test as you would in trigonometric functions. Here you succeed in the horizontal line test. But if you look at this function right here and you limit the domain from 0 up to infinity or from minus infinity up to 0, now you can establish a horizontal line test to be successful, because in all of these instances you can have a one-to-one relationship. In addition, for these inverse functions, you always have some sort of symmetry about the y equals x line, imaginary line. You'll have a symmetry about that. It's important to understand this concept as we get into this inverse hyperbolic subject. There are three basically inverse hyperbolics you should be well familiar with. Those are inverse hyperbolic sine, inverse hyperbolic cosine, and inverse hyperbolic tangent. The other three are just not that important. If you have something like this, y or f of x is equal to inverse hyperbolic sine. You see that minus 1, it means it's an inverse. You could also read this as this by taking this on the other side. If you look at the graph of a hyperbolic sine, we're not talking about hyperbolic inverse sine, but regular hyperbolic sine. This is a graph of a hyperbolic sine. Look at the domain. The domain here is minus infinity up to positive infinity. The range here is minus infinity up to positive infinity. If you do the inverse of this, and now you're looking at this right over here, sine h minus 1x, the graph becomes this. Again, here the domain happens to be minus infinity to positive infinity, and the range here happens to be minus infinity to positive infinity. You can appreciate it because these are similar domain and ranges, but the domain and the range flip. What was a domain of one becomes a range of the other. What was a range of one becomes a domain of the other. If you were to look at these on the same graph, you have a y equals x, you could see a mirror symmetry develop, and you could see it like this along this y equals x. This one right here is my sine hx, this here is my sine h inverse x, and you always have a symmetry about this y equals x. So that right here is this curve right here, sine hyperbolic inverse right here, and you should be familiar with this. The inverse hyperbolic cosine is interesting because it does not have a one-to-one inverse function develop from it unless you limit its domain. The basic hyperbolic cosine graph is this, having a y-intercept of 0, 1. This right here is cosine hx. If you look at this in terms of the domain, it's minus infinity up to infinity, and the range is 1 up to infinity, including this 1. But you cannot have a one-to-one because the horizontal line test fails. It crosses at 2 points. If you, however, limit the domain such that now you can have a one-to-one function, the new domain, let's say new d, is now basically 0, infinity, including 0, and now that's a new domain. To show you the inverse hyperbolic cosine graph, it's not hard. You just have to think about symmetry around y equals x imaginary line. If this right here is 0, 1, the inverse here will start from 1, 0, and it will look in this direction. It will have a mirror symmetry about this y equals x imaginary line. In this instance, the domain over here is going to be the range of this 1, infinity, and you'll see it going from 1 up to infinity. And now the range is going to be what was a new domain over here, 0, infinity, and you can see it 0 but going upwards towards infinity, and you see there's a range and domain flip between the two. This right here is your basic hyperbolic cosine, this right here is your inverse hyperbolic cosine, and you should be familiar with this. Here we have the inverse hyperbolic tangent and the basic hyperbolic tangent. You can see how you can look at either or. Here's your inverse, here's your regular. Like the hyperbolic sine, the hyperbolic tangent is an easy one-to-one function along its entire domain, so you don't have to do any domain limitation or restriction to develop that inverse. The basic hyperbolic tangent has an easy graph, and we've shown you this in a previous video. It has y equals 1 and y equals minus 1 horizontal asymptotes, and the curve looks something like this. Here the domain is minus infinity up to infinity, and the range is minus 1 up to 1, not including minus 1 up to 1, because it's limited here between the two asymptotes, the horizontal asymptotes. The inverse hyperbolic is interesting. Inverse hyperbolic tangent, you will have a domain and range flip. In this instance, your curve will become like this: x equals minus 1 and x equals 1 asymptotes, vertical asymptotes, but your graph becomes this. Again, if you were to mirror both of these on the same graph, you would have a clear one-to-one symmetry and one-to-one relationship across a y equals x imaginary line. But in this instance, your domain, you can see what it is. It's minus 1 up to 1, limited by the vertical asymptotes. The range over here is minus infinity up to infinity. So in all instances, when you have a function and its inverse, the domain and the ranges flip. What is the domain here becomes the range here, what's the range here becomes the domain here, and you see that. Now we look at the most important calculus aspect of inverse hyperbolics. For the inverse hyperbolic sine, inverse hyperbolic cosine, and the inverse hyperbolic tangent, and that's how we come about with the derivatives of these three functions. If you have y equals inverse hyperbolic sine x, you can rewrite this as this: sine h y is equal to x. There's nothing wrong with you writing it in this way, because if you solve for y, you take this on the other side, you get the inverse function, and you do implicit differentiation of this. You know what implicit differentiation is, we've seen it. You have d over dy is sine h y, and then dy over dx is equal to derivative of this x. The derivative of sine h, hyperbolic sine, is always cosine. And then you have dy over dx is equal to 1. You know, in these instances, you're solving for dy over dx, which is synonymous with this y prime. A derivative with respect to y is equal to 1 over cosine hy. This is what we have. But if you think back to this hyperbolic identity, cosine h square x minus sine h square x is equal to 1, and you've seen this and I've shown it to you. The most important hyperbolic identity you solve here for cosine hx. Cosine hx is equal to 1 plus sine h square x. You solve for the actual cosine h, you take the square on the other side, and you get a square root. If you look everything here in terms of y, it's cosine hy is equal to square root of 1 plus sine h square y. X's and y's, it doesn't matter what variable you're looking at, and you can substitute this for this, and you get 1 over 1 plus sine h square y, and you can say you're looking at something which looks like 1 plus x square. So if someone were to ask you what's the derivative of inverse hyperbolic sine x, you would say it's 1 over root of 1 plus x square. And if you think back to the derivative of basic hyperbolic sine hx, the derivative of sine hx, the non-inverse function, was just cosine hx. This is something you should know because you could see it. Let's look at the derivative determination for this hyperbolic cosine inverse, or you can say inverse hyperbolic cosine function, with the restricted domain values larger than 0, so you have no horizontal line test failing that curve. You have a restricted domain. everything starts with you looking at this equation in this form. You take the hyperbolic inverse on the other side, it becomes cosine hy equals x. You do implicit differentiation of this. You have d over dy cosine hy dy over dx is equal to derivative of this x. With this cosine hy, you'll have sine hy coming out of it, because the derivative of cosine h is hyperbolic sine. Here you get a 1. You solve for this dy over dx is equal to 1 over sine hy. You think back to the same identity I just put out here, cosine h square x or y minus sine h square x or y is equal to 1. You solve here now for sine hy minus sine h square y is equal to 1 minus cosine h square y. Flip the signs around. Sine h square y is equal to cosine h square y minus 1. You solve for the sine hy. You take the root of this. You get cosine h square y minus 1, which you can substitute right here. You get 1 over cosine h square y minus 1. If this cosine h square y represents a variable, and that variable were to be x, you can say you are looking at 1 over x square minus 1 in a root. So now you know the derivative of inverse hyperbolic cosine is 1 divided by square root of x square minus 1, but you know from before that the derivative of the basic hyperbolic cosine is always equal to a hyperbolic sine. So now you know the derivative of the inverse hyperbolic cosine, and this right here, you should remember that. Our video here will end with the determination of the derivative of the inverse hyperbolic tangent function. If y is equal to inverse hyperbolic tan x, you can solve for that x and say hyperbolic tan y is equal to that x. You look at this equation here and you do its implicit differentiation, and we know how to do it, and let's do it. We remember the derivative of tan hy is secant h square y, because you know derivative of tan hx is secant h square x, hyperbolic secant square. You're doing d over dy tan hy dy over dx is equal to derivative of that x. You know you're always solving for dy over dx. Derivative of this, we remember from our hyperbolics derivative video, is secant h square x or secant h square y, depending on your variable you're looking at, is equal to 1. You solve for dy over dx is equal to 1 over secant h square y. Now we have to somehow convert this into a derivative using an identity. We know cosine h square x or y, let's use y, minus sine h square y is equal to 1. If we divide everything by cosine h square y, we get a 1 minus tan hyperbolic square y is equal to secant h square y. We're looking at this right here, it can substitute for all of that. So you get 1 over 1 minus hyperbolic tangent square y. That's why you have to remember some of these hyperbolic identities, they come into play over here. If you think of this in terms of a variable, you're looking at 1 over 1 minus x square. This ends up being the derivative. So anytime you see the inverse hyperbolic tangent function, you should be thinking of its derivative as being 1 over 1 minus x square. So that's something you should know. And likewise, you know the derivative of the basic hyperbolic tangent is equal to secant h square x, or you can say is equal to 1 over cosine h square x. Either or is an acceptable answer. This right here, secant h square x, is a better answer. So keep in mind, we've looked in this video at, again, a quick review of functions and in their inverses. We've looked at the graphs of these three hyperbolics: hyperbolic inverse sine, hyperbolic inverse cosine, hyperbolic inverse tangent. Then we've looked at their derivatives. Keep in mind, these derivatives are not hard. You can always refer back to a reference sheet. You don't have to memorize any of this. It's going to be 1 over root of 1 plus x squared. Anytime you're seeing this hyperbolic inverse cosine, you're looking at 1 over root x squared minus 1. And lastly, these three being the most important, inverse hyperbolic tangent, it's going to be 1 over 1 minus x squared. So these are the three derivatives you should be familiar with. Lastly, remember this: any function, to have an inverse, it must pass the horizontal line test, meaning it must show and demonstrate a one-to-one relationship between the domain and the range. If there is no one-to-one relationship between the domain and the range, you may have to restrict the domain, find that portion of the function where you have one-to-one relationship, examine and focus only at that particular point, and then you can develop an inverse. And these inverses and these original functions are usually symmetric about the y equals x imaginary line, and you have a domain and a range which flips between the two. The domain of one becomes the range of the other, and the range of one becomes the domain of the other. That's it for this video. Thank you for watching. Have a nice day.